All right, so hello. This is a longer video talking about my master thesis, which is matrix multiplication free model for image classification. There's another 10-minute video talking about with the same slides and talking about the same project, but it's a 10-minute video, which is like not a lot of time to explain everything. So the idea for this video is just to try to explain the same, but slower and with more detail and with more time, so you can guys understand better. Let's start with the introduction. What is a matrix multiplication free neural network? So the idea behind the matrix multiplication free neural network is to, instead of using multiplications from the chip, use only the others, which are are more simple and they use less energy. So in theory, if you take the chip and you don't use the multipliers and you only use addition and subtractions, you should be able to use less energy and also less latency. So that's the main idea behind matrix multiplication free models. If you are able to have the same neural network that works with the same accuracy but doesn't use multiplications, then you should be able to save energy with that network. So okay, going back to the standard dense layer from a neural network that uses matrix multiplications. So we have the input X, and we have the weight matrix and the output Y. So this means that in one layer, we multiply the input by the weights and we can compute the output. If we using matrix multiplications, what we can do is, instead of only doing this with one input, we can have more than one X. So in this case, X has 4 coordinates. And in the input matrix, we have 2 times 4 matrix, which means that we are using 2 inputs. And then we are multiplying this by the weights, and we are mapping 2 outputs. In this case, the output is dimension 6. We have 2 outputs, so that's why the output is 2 times 6, and then the weight is 4 times 6, which is mapping each of the inputs in the output space. So, okay, how can we make this? How can we remove then all these matrix multiplications from here? So the idea from matmul free is that instead of using full precision weights, you use ternary weights. So in this case, as we can see here in the screen, all the weights are either -1, 0, or +1. And in this way, instead of having a multiplication, you just check the value of the weight. So if the value of the weight is 1, the output is going to be the same as the input. If the value of the weight is 0, the output for that is going to be 0. And then if the value of the W is -1, then it's -x. So in this way, we can compute the output by a series of additions and subtractions without having to use multiplications. So this would be relevant for the if this works, then it means that we have the same network that uses less energy, which is also cheaper. And then also means that if we have the same networks that can be used with less energy, we can use it in robots or edge devices and places where there's no so many energy. So in this way, the goal for this project is to try to apply matmul-free to a vision model, specifically to image classification, which is the simplest task. So like in the end, the goal of the project is to, okay, first train a baseline neural network with matrix multiplication, and then train exactly the same network, but replacing the dense layers with matmul-free layers, and compare both and see what happens. Well, and then in the end, a little spoiler, is also like trying to improve the matmul-free model, like once both are trained. So let me show you like how did I do this? I used the CFAR10 dataset, which was pretty simple. 10 distinguishable classes, very different from each other. 32 by 32 pixels RGB images. I was using low resolution, so I could like test faster and easier. And then let's say that I wanted to simplify everything, so I was able to give an easy task to the matmul-free network. And then also this dataset has like enough images for training, 5K per class, and then 1K per validation. The model structure that I use is YOLO v1, which is like a very simple structure that uses convolutional layers. So in the YOLO v1 paper, the structure is originally for object detection, but before training it for object detection, they train it for object classification. So that's exactly what I replicated. And the network in total, it had like 22.4 million parameters. Okay. And now I also want to explain here more details about how how the matmul and how the matmul-free is implementing in the hardware, because while working in the project, I was like, I was a little bit confused, and then I found out what I'm gonna tell you now. So let's start with the matmul implementation on GPU. So the GPU has tensor cores. In the GPU that I was using, the NVIDIA GeForce RTX 3090, it has 336 tensor cores, and each of these tensor core is capable of doing a matrix multiplication, the one that we can see in the image, in one cycle. So it's like doing all this it's multiplying this A times B plus C, and these are matrices of sizes. Well, here they are given 8 times 8, and then the A and B are 8 times 4 and 4 times 8. And each of these values are in FP16, so half precision. So it's able to do this matrix operation in one cycle. And and the sizes here, these ones are specific for this GPU, and also the precision it depends on the model. So for this, these are the numbers for this specific model. So this means if we make some basic maths, if we multiply the number of tensor cores, which is 336, by the number of operations per tensor core, so the number of operations per tensor core is the number of multiplications and additions of one number times another one, or one number plus another one. So for example, here, when we multiply this row by this column, we have 1, 2, 3, 4 multiplications, and then 3 additions, right? So that's the first 4 here, and the 3 additions here. And then we have it multiplies it by 8, because, well, in this image we have fuck, this is wrong, man. Oh no, it's right. It's right. Okay, no, okay, no, it's good, no problem. The the matrix size here is 8 times 4, so this is 8 rows, 4 columns. So the number of columns here is fine, but the rows is bigger. And here B is 4 rows, so these rows are okay, but then we have 8 columns. So this means that we have 4 multiplications, 3 additions, that was fine. And then here we multiply by 8 because we are doing like 8 columns. And then we are doing the same by 8 rows. So this is the number of multiplications, this is the number of additions, and then once we compute A times B, we have to add it to C, which is a matrix of size 8 times 8. So this means that we have 8 times 8 additions. So this means that in a single A times B plus C, we have 512 multiplication or addition operations. And then if we multiply it by 336, then we have that in the single cycle, the GPU is able to compute 172,000 operations in one cycle. So that's like what the GPU is capable of doing when using matmul. So this means that for the standard dense layer, we can use this for our matrix multiplications. So in theory, we can use 172K operations per cycle, which is pretty good, and the matmul is happy. But then for the matmul free layer, this one is not. I mean, the face here is not very happy because for the matmul free layer, you need to go check in all the weights. Like you have to go checking if the values are either 1, 0, or -1 in order to compute the output x0 or -x. So this means that when you go checking one by one, you are limiting yourself to 1 operation per cycle. So this means that if you try to run matmul free on GPU, you are limited to 1 operation per cycle, which means that you are competing against you are competing against 172K operations per cycle that is being efficiently used in the matrix multiplication layer. So to do this efficiently with the matmul free, what you can do is use dedicated hardware that is able to compute like in a single clock in a single cycle is able to compute them, like to check all the if statements in a single cycle. So this is possible in some application specific circuits or FPGAs, where you can directly map the binary weights, and then you can do like once you have the input, if the value of the weight for that input is 1, the gate is gonna be open. If it's 0, it's gonna be closed, and if it's negative, there's gonna be like an inverter there. So that's how it's possible. But then for training, the matmul free model can be trained on a GPU. So here we can okay, we have this very good hardware which already exists, which is the GPU, which is capable of doing 172K operations per cycle. So it would be like it's like a good idea to use it that once that you have it, right? Like you have this computing capability, so okay, let's use it for training. If we don't use it, then the training is gonna be so much slower, so why not use it? So the idea here for training a matmul-free model in a GPU is by doing quantize-aware training. So this means that training is the process of doing forward pass, computing the loss function, and then doing the backward pass. And here, while doing the backward pass, internally you are computing the gradients, and then you are updating the weights, which normally they are in floating point, in full precision representation. So here you do the same. You internally save the weights in full precision. However, in forward, you quantize the weights. So you have the full precision weights, and you quantize them to, in this case, ternary. If we look at the weight quantization function here, what you do first is S times W. So it's like W divided by the mean of the absolute value of all the weights, and then you clamp you round this between -1 and 1, and then you clamp it. So this means that this means that you are making the weights ternary basically, and then you multiply it again by 1 divided by S, which is you multiply it by the mean. So the value of the weights will be either minus mean of W, 0, or mean, if that makes sense. Yeah, and by doing this in the forward pass, then in the backward pass, you also need to make some modifications, which, well, I can show it in the report. If we go here, so in the forward pass, you quantize the weights, and then in the backward pass, you also have this customized backward pass, which is taking into account the quantization. So yeah, that being said, more or less, an overview is that okay, this is a little confusing because in reality you are training a matmul-free model on the GPU, and the GPU itself in the hardware is using matrix multiplication. So I mean, in reality you are training a matmul-free model, but when you are doing the forward pass in the GPU, it is not really matmul-free in the hardware level, you know. When you compute this multiplication here, you are using the GPU and you are using the matrix multiplication from the tensor cores. So in the hardware level, it's not matmul-free. However, you are training with ternary weights, which later, when the training process is finished and you map it into the dedicated hardware, then it will come the real matmul-free in the hardware level. So yeah, here following the bullet points, you are using while training, you are using the GPU, so you are taking the profit from the 172 case operations per cycle. You are also using the matmul in hardware, so it's not real matmul-free. then when training, you are saving the full precision weights, and you are making it ternary only in the forward pass. We are training with quantized aware training in the forward and in the backward. And yeah, well, this one I already said that the in the forward, like the matmul free is only in the forward when you quantize the weights. So then the idea here is that once you train with the quantization over training, and you make sure that your model, your matmul free model, is able to achieve a certain accuracy, then you can map it to dedicated hardware. And here you will have the same accuracy to which you have trained previously, but here, as you are really doing the matmul free in the hardware level, is where the energy reduction will come. So in theory, like the main goal from matmul free is to reduce the multiplications in the hardware level to reduce the energy. But here, while training, you are not removing the multiplications because you are still using the GPU. However, then when you do the inference in the dedicated hardware, this is when you really remove the multiplications, and this is where you need to measure the energy and see how much it goes down. However, in my project, I only did the training part, so like the number for me, the most important number that I was measuring is the accuracy, to make sure that the matmul free model matches the baseline. Well, a small spoiler, it didn't match, and I was doing like all the efforts to bring the accuracy from the matmul free model to bring it up, but yeah, I wasn't able to match the same accuracy as the baseline. But the idea would be like, or at least for me, once it matches, then you make sure that, okay, now the accuracy is good enough, and then you make it work in the dedicated hardware, and here you should have the same accuracy as you have trained for. And here, if you, like in theory, if you measure the energy here, it should be lower than in the GPU because you are not using the multiplications. So, all right, let me show you some results now. So, okay, this is a summary table. So my project, it was divided like in, well, I had like two models, the baseline model and the matmul free model. So the first thing that I did is to train the baseline model and make sure that it was good enough. So here, the first phase is hyperparameter tuning. So here I was basically changing the batch size, the learning rate, the learning rate scheduler, the weight decay, different hyperparameters to try to increase the accuracy of the baseline model. And the best one achieved 85%. I can show you a little bit in the report. The report is available on my GitHub, so if you want to take a look at it, if you go to the appendix, you have all the experiments that I did. So if you go to baseline model hyperparameter tuning, these are all the experiments, like training while measuring the validation accuracy while training. And here I have like all the details that I try with each, and the best one is 85%. Then after this, what I tried is like, okay, what happens if I take this model and just make it ternary in inference? Is it gonna work? So no, it didn't work. It was 10%, which means like random guessing in a data set with 10 classes. So this means that the quantization our training is necessary, and if you don't do it, it's just gonna fail. So okay, after training the baseline and making sure that it worked, and having an accuracy of 85%, which was the number to beat, I started training the Matmul-free model. So the first phase here is hyperparameter tuning. In this phase, similarly to the previous one with the baseline, it was changing the learning rate, batch size, weight decay, learning rate scheduler, these kind of hyperparameters, which for the Matmul-free model are different. So if I go here, if you go to the appendix in the report, you have all the trainings here. Yeah, okay, there are a lot, but it's just to show it in the table. You can see it better, all the variations. So what at the beginning I started with around 40%, which was pretty low. After some hyperparameter tuning, I was able to bring it up to 60%. So that was the first phase. Then the second phase is with modifying the number of channels. So this means that you have a model which has which had the structure like YOLO v1. The YOLO Matmul-free model has the same structure, but instead of using convolution and layers and like densely connected layers, you have the equivalents, but using Matmul-free. So just using the same structures and same layers, you can change the number of channels. You can increase it or decrease it. So here what I did in this second phase is modify the number of channels. So I was just making the like the number of channels bigger or smaller, modifying the number of trainable parameters of the network. So like, I mean, in theory, if you make the number of channels smaller, then the network should be worse or the accuracy should be worse. And if you make it bigger, it should be better. And this is what the experiments proved. So here alpha is like the number that I'm multiplying the number of channels. So this means alpha 0.5 is that the number of channels is divided by 2 in all of the channels. And if alpha is equal to 2 is that the number of channels is the double of the original channels. And here you can see that the parameters with 0.5 is lower, and that if the network is bigger, then you have more parameters. And the important part here is to look at the accuracies. So the validation accuracy was lower for smaller networks, and it was a little bit, not too much, like 3% more bigger for the bigger network, but the training time, it was like so much slower, and also the gigabytes that was taken for like the memory for the GPU, it was like 3 times more. So yeah, the conclusion is that the accuracy went up, but the training time was also pretty huge. So yeah. Then the third phase is the modifying the weight initialization, and this one gave me a surprising 6% more. So here, modifying the weight initializations means that when you initialize the network, at the beginning it was initialized with random weights between -1 and 1 with a normal distribution. So changing the initialization, what I was doing is scaling down or up this number. So instead of instead of initializing the weights between -1 and 1, they would be initialized, I don't know, between -3 and 3, or between -0.5 and 0.5. And here what I found, if you go to the appendix, basically with making the scale bigger, so initializing the values with bigger numbers, it would make the results worse, but then reducing it would make the results better. So with 0.2, I achieved a 66%, which was a little surprising for me. And then the last experiments I did is increasing the quantization levels. So this means, okay, what if instead of making the matmul-free model ternary, we make it quinary, like with 5 possible weight values, or septenary or nonary. So in theory, the more weights that you have, it should be better. But in the results, like after training, the best one that I achieve is here for 5 levels. So this means that there are, like you have 5 weights. So this means that instead of having -1, 0, and 1 ternary weights, you have something like -1, -0.5, 0, 0.5, and 1. Yeah, if that makes sense. All right, so going back to the presentation here, now what I did is take the best one from the baseline and take the best one from the matmul-free and compare them. So here we have the training while like the validation accuracy while training. We can see that both converge. The baseline has like a weird spike, but then it corrects, so it's fine. And then you still have 18 points of difference, which is a lot, but that's like the outcome from this project. Then here you can see the dynamics of the neural network that are pretty different. The best matmul-free models needs a higher learning rate, and then it was very well. Here it's also using a cosine scheduler, and it was very useful, this jump here. So in the middle of the training process, you use half the learning rate, and this one kind of helped. I'm not sure why, but it just worked. So yeah, and here in the baseline, instead of using cosine, it's using a learning rate scheduler on plateau, which is basically keeping constant the learning rate, like flat, and when the validation accuracy stops improving, it's gonna reduce the learning rate, and then it keeps it constant until the validation accuracy doesn't improve, and then it just goes reducing it, and so on and so on. Now if we look at the average confidence number for both models, for when the prediction is correct and when it's incorrect, we can see that the blue one, the baseline, the values are higher. So this means that when the prediction is correct, I mean, it's almost like 0.9 is very high. But when it's incorrect, like the class that is predicting has like 65%, so it's not so sure if it's that or another one. And then the matmul-free, the matmul-free follows a similar logic, so it's more sure when it's correct rather than when it's incorrect. But if you compare it to the baseline, those values are lower, so the baseline is more sure of what it's doing. at least in the correct one. Then if we compare the confusion matrix from both, they are pretty similar. Like we have this clear diagonal, but then in general the matmul3 is like more confused, and yeah, we can see that the diagonal here is not so strong. We can see some confusion in this area for the baseline model, so basically between cats and dogs, and here is like stronger, like a similar pattern but a little stronger. And then, well, here we cannot almost even notice that there is a little confusion here, like in these corners, and here is just stronger. So this is between airplanes and ships, and between trucks and automobiles. Yeah, finally the weight distribution from both models. So here for the baseline is in blue, and we can see that the values are like distributed very close to 0. And then for the matmul3, there are two colors, the orange one and the red one. So the orange one is the raw values of the weights without being quantized. Remember that when we train a matmul3 model, in reality, we are saving the floating point values of the weights. So these are the orange. These are the orange weights in the graph. But then in the matmul3 in the forward is when we are quantizing with the weights. So we are quantizing to ternary, quinary, septenary, and remember that for this one the best matmul3 was quinary, so it has like 5 quantization levels, and here they are the values. So in all of them they are like symmetric, and the more like there are more 0 values than the positives or negatives. Yeah, so here the conclusion is that the matmul3 model is trainable for image classification. It works. It's better than the 10%. That means that it's just a random choice. So that's like a good point. Then the not so good point is that the accuracy is still far below the matmul, the baseline. And then some future work here, which is pretty like obvious from yeah. So it's just like a well, the first thing is just to keep working and improve the accuracy of the matmul3, testing different ideas. Then from my point of view, once the matmul3 accuracy is achieved, once you are able to show that the accuracy from the matmul3 is like very close to the baseline or almost the same, then it makes sense to take a dedicated hardware, map the matmul3 model, and then start measuring the energy. Then it would be also interesting, once this is like proven, that once you show that for classification we have the same accuracy, then we are able to measure the energy and we can see that it's lower. Like this is all in theory, you know. Then it would be interesting to measure. Once you do this, it would be interesting to extend to other vision tasks. So for example, the most immediate one is object detection, but also other ones like segmentation or pose estimation or like more complex things. Then also something interesting that would be cool to do, instead of using YOLOv1, which is the simplest one that I have used like as a proof of concept, use more state-of-the-art architectures. Here it kind of makes sense to like let's prove it first. Let's see if it works for the YOLOv1 architecture, and then for the state-of-the-art architectures which are more complex, you can replicate the same process of the training. And then the last one, this one is using hybrid architectures, which means in the same neural network, maybe you can use some layers that are matmul and are running on a GPU, and some other layers that are running on or matmul free on a dedicated hardware. So that would be like interesting future line to research. So yeah, I think that's everything. I hope this video, like the longer version, was kind of helpful. Yeah, I repeat myself, but the intention from this longer video is just to be able to explain everything a little more in detail and with more time than the short video. If there are like things that are not very clear, you can just I don't know, put something, put a comment or something on YouTube or GitHub or whatever. And also, if some of my explanation was like pretty bad, maybe reading the report is gonna be more helpful. So yeah, I don't know. I hope it was helpful, and thank you for listening or watching.